Hello, in this lecture we'll find out the area of the green shape using two different methods. In the drawing we have two circles. The center of each circle, each circle is passing through the center of the other circle. This circle is passing through the center of this circle, and this circle is passing through the center of this circle, and we know that the radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So first of all, I will explain to you two terms. The first term is sector. The sector is the area that is bounded by two radiuses. This is the first radius, this is the second radius, and the arc that is included between those two radiuses. So sector AOB is the shape, is the green shape, and again sector AOB is bounded by the radius AO, the radius OB, and the arc AB. Okay, so this is sector AOB. The green shape is sector AOB, and the area of sector AOB equals to pi r squared times 60 degrees over 360 degrees. Okay, the angle between the two radiuses could be any other angle. I just gave an example of a specific sector. So the area of a sector is pi r squared, when r is the radius of the circle, and times the angle between the two radiuses over 360 degrees. In our case, the angle between the two radiuses is 60 degrees, so the area of this sector equals to pi r squared, when r is the radius of this circle, times 60 degrees over 360 degrees. Okay, the area of shape AOB equals to pi r squared minus 60 degrees over 360 degrees. So this is the definition of a sector, and the area of a sector is pi r squared, that is the area of the circle, times the angle that is between the two radiuses over 360 degrees. Okay, so this is the definition of a sector. And we have also another term that is actually segment. Here, segment is the area that is bounded by arc AB and the chord AB that is attached to this arc. Okay, so chord AOB is this green area, and it is the area that is bounded by the chord and by the arc and the chord that is attached to this arc. So it is the area that is bounded by arc AB and chord AB that is actually attached to this arc AB. Okay, again, the area that is bounded by an arc and the chord that is attached to that arc is defined as a segment that is actually inside a circle, and the area of this circle will be equal to the area of sector AOB minus the area of triangle AOB. You can see it easily that if you subtract from the area of sector AOB, if you subtract from it the area of triangle AOB, you will get the green shape that is actually segment AB. Okay? Again, the area of segment AB, the green shape, equals to the area of sector AOB, this is actually this area, minus the area of triangle AOB. So if you subtract from the area of sector AOB the area of triangle AOB, you will get the area of segment AB, that is the area of this green shape. Okay? So, in the next step, we will do construction. We'll actually join together. First of all, we will define the center of this circle as point P, and we will define the center of this circle as point Q. We will define the first intersection point of those two circles as point A, and we will define the second intersection point of those two circles as point B. In the next step, we will join together points P and B by a straight line. Actually, line segment PB is the radius of this circle because of the fact that line segment PB starts from point P, that is the center of this circle, and ends at point B, that is a point on the circle itself. Therefore, PB is the radius of this circle, that is to say, it equals to 5 units, because it is given us the question that the radius of those two circles is equal to 5 units. In the next step, we will join together points Q and B by a straight line. Here, line segment QB is also the radius of this circle because of the fact that it starts from the center of the circle, that is to say from point Q, and ends at point B, that is a point on the circle itself. Therefore, QB is the radius of this circle, that is to say it equals to 5 units. In the next step, we will join points A and Q together by a straight line. And again, line segment AQ is the radius of this circle because of the fact that it starts from the center of this circle and ends at point A. That is a point on the circle itself. Therefore, it is the radius of this circle, and it equals to 5 units, of course. We will join points A and P together by a straight line. And again, AP is defined as the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point P, and ends at point A, that is a point on this circle itself. Therefore, it is the radius of this circle, that is to say it equals also to 5 units. So here, we created here quadrilateral APBQ. Quadrilateral APBQ is defined as a rhombus. I will write it down. Quadrilateral APBQ is a rhombus. A rhombus is a quadrilateral that all of its sides are equal to each other, and as you can see here, rhombus APBQ has 4 equal sides. All of its sides are equal to 5 units. So quadrilateral APBQ is a rhombus, and will join points A and B together by a straight line. Actually, line segment AB is the first diagonal of rhombus APBQ. Then we will join together points P and Q by a straight line. PQ is the second diagonal of rhombus APBQ. PQ is also the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point P, and ends at point Q, that is the point of this circle itself. Therefore PQ is the radius of this circle, and therefore it equals to 5 units. So here we have two diagonals of rhombus APBQ. The first diagonal is AB and the second diagonal is PQ. And we have two characteristics of the diagonals of a rhombus. I will write it down. The diagonals of a rhombus the diagonals of a rhombus are, they have two characteristics that are relevant to this question. The first characteristic is that they are perpendicular to each other. I repeat again, the diagonals of a rhombus are perpendicular to each other. That is to say, the diagonal AB is perpendicular to PQ and the diagonal PQ is perpendicular to AB. It means that we have here four right angles So we have four right angles, 1, 2, 3, 4. We will define the intersection point between diagonal AB and diagonal PQ as point M. And the second characteristic of the diagonals of a rhombus is that they bisect each other. Again, the diagonals of a rhombus bisect each other. That is to say, the diagonal AB bisect PQ. That is to say, PM equals to MQ. PM equals to MQ. So, if we define if we define PM as x, MQ will be also equal to x because of the fact that PM equals to MQ. And we also know that the diagonal PQ bisect AB, the diagonal PQ bisect the diagonal AB, that is to say AM equals to MB. AM equals to MB. AM equals to MB. So here x plus x is PM plus MQ, that is to say x plus x equals to PQ, x plus x equals to PQ, but PQ is the radius of this circle, that is to say it equals to 5 units. So PQ equals to 5 units, so we got that x plus x equals to 5, that is to say 2x equals to 5. We'll divide this equation by 2 and we will get that x equals to 5 over 2. X equals to 5 over 2 units, so x equals to 5 over 2. We will substitute x by 5 over 2. PM that equals to x equals to 5 over 2 units, and MQ that equals to x also equals to 5 over 2 units. In the next step, we will focus on 4 right triangles, triangle APM, triangle AMQ, triangle BMQ, and the right triangle, triangle BPMB. On those 2 right triangles, if we focus on those angles, if we focus on those 4 angles, then in those 4 triangles, that is to say the right triangle, triangle APM, the right triangle, triangle AMQ, the right triangle, triangle MQB, and the right triangle, triangle PMB. Then we know that cosine theta of those 4 angles, 1, 2, 3, 4, cosine theta of those 4 angles will be equal to 5 over 2 over 5. Again, those 4 angles, 1, 2, 3, 4, here cosine of those 4 angles, cosine of those 4 angles equals to 5 over 2 over 5. 5 over 2 over 5, 5 over 2 over 5, 5 over 2 over 5. Okay, so on those 4 triangles, cosine theta equals to 5 over 2 over 5. 5 over 2 over 5 equals to 5 over 5 times 2. 5 over 5 is 1 over 2. So we found out that cosine theta equals to cosine theta on those four triangles equals to 1 over 2 cosine theta equals to 1 over 2, and if cosine theta equals to 1 over 2, it means that theta equals to 60 degrees. So we actually found out that all those four angles are equal to 60 degrees. So we can write here that this angle equals to 60 degrees, this angle also equals to 60 degrees, this angle equals to 60 degrees, and this angle also equals to 60 degrees. Okay? In the next step, we will prove that those two triangles can go into each other. That is to say, we will prove that triangle APB congruent to triangle AQB. Okay, we prove that those two triangles can go into each other. First of all, we know that AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. We also know that PB equals to BQ also equals to 5 units. PB equals to BQ, and they are also equal to 5 units. And we also know that AB is a common side, so AB equals to itself. AB equals to AB. AB equals to AB. It's a common side that belongs to both triangles. So we actually proved that triangle APB congruent to triangle AQB according to side rule. Okay, we proved that all sides of triangle APB can go into all the sides of triangle AQB, therefore those two triangles can go into each other. And from the fact that those two triangles can go into each other, we will conclude that they have also the same areas. So the area of triangle APB, the squared bracket is the sign for the area of triangle APB equals to the area of triangle AQB. Okay, so those two triangles have the same areas, and what is the area of sector APB? The area of sector APB, this sector will be equal to, actually I'm talking about the area of segment APB. The area of segment APB, this half circle, the area of segment APB will be equal to the area of sector APB, and will be equal to the area of sector AQB minus the area of triangle AQB. I will write it down. Actually, we found out that the area of segment APB the area of this segment the shape that is half, it is like half circle, the number of segment APB equals to the area of sector AQB, this sector, minus the area of triangle AQB. I repeat again, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. And what is the area of sector AQB? The area of sector AQB equals to pi r squared times 60 degrees plus 60 degrees is 120 degrees over 360 degrees. I repeat again, the area of sector APB equals to pi r squared, r equals to 5, pi r squared times 60 degrees plus 60 degrees is 120 degrees over 360 degrees. I repeat again, the area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. R equals to 5, so r squared is 5 squared. 5 squared is 25. So we have here 25 pi and 120 degrees over 360 degrees is 1 over 3. So it is 25 pi over 3. So the area of sector AQB equals to 25 pi over 3 square units and what is the area of sector APB, the area of this sector, sector APB, the area of sector APB will be equal to pi r squared times 60 degrees plus 60 degrees is 120 degrees, 120 degrees over 360 degrees. Again, the area of sector APB equals to pi r squared times 120 degrees over 360 degrees. So we found out that the area of sector APB equals to r equals to 5, so r squared is 25. So we have here 25 pi and 120 degrees over 360 degrees is 1 over 3. So we found out that the area of sector APB also equals to 25 pi over 3 square units. So because of the fact that the area of sector AQB also equals to 25 pi over 3 square units, So the area of those two sectors are equal both to 25 pi over 3 square units. Therefore, we will conclude that the area of sector APB is equal to the area of sector AQB and it is equals to 25 pi over 3 square units, and we have already found out that the area of triangle APB is equal to the area of triangle AQB. So we define the areas of those two triangles that are equal to each other as x. Okay? And what is the area of segment APB? The area of segment APB the area of these segments, the shape that is like half a circle, the area of segment ABB will be equal to the area of sector AQB minus the area of triangle AQB. And repeat again, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. So the area of sector AQB, we have already found out that it equals to 25 pi over 3 square units, and the area of triangle AQB the area of triangle AQB is equals to the area of triangle APB, and it equals to x. So it is the area of triangle AQB equals to x. So actually we found out that the area of segment APB equals to 25 pi over 3 minus x square units. And what is the area of segment AQB? The area of segment AQB the area of segment AQB, the area of this circle, the shape that is like half a circle, will be equal to the area of sector APB, the area of sector APB minus the area of triangle APB. I repeat again, the area of segment AQB equals to the area of sector AQB, the area of segment AQB equals to the area of sector APB minus the area of triangle APB. But we have already found out that the area of sector APB equals to 25 pi over 3 square units, and the area of triangle PB equals to X. So we found out that the area of segment AQB equals to 25 pi over 3 minus X square units, and the area of segment APB also equals to 25 pi over 3 minus X square units. So we can conclude from those two lines that the area of segment APB is equal to the area of segment AQB so the area of segment APB, this segment, equals to the area of segment AQB, this segment. So therefore, in order to find out the area of this green shape, we will multiply the area of segment AQB by 2, and we will get the area of this green shape because of the fact that those two areas are equal to each other. So if we multiply the area of segment AQB by 2, we will get the area of this green shape. Okay, so I will write it down. So the area of the green shape, the area that we are looking for, the area of the green shape, equals to 2 times the area of segment AQB. 2 times the area of segment AQB. So the only thing that is left to find is to find out the area of segment AQB, and in this way we multiply it by 2 and we'll get the area of the green shape. Okay? So we have already found out that the area of segment AQB equals to 25 pi over 3 minus X. So we will multiply the area of segment AQ by 2 and we will find out the area of the green shape. Okay, so the area of the green shape equals to 2 times 25 pi over 3 minus X. Okay, and X is the area of triangle AQB that equals to the area of triangle APB. So we have to find out the area of this triangle, triangle AQB. The area of triangle AQB equals the area of triangle AQB equals to the base of the triangle that is actually AB times the height to the base that is actually AMQ, all divided by 2. I'll repeat again. The area of triangle AQB equals to the base of the triangle that is actually AB times the height to the base that is MQ over 2. Okay? And we also know that AM equals to MB. AM equals to MB. Therefore, we'll find out the value of AM. We'll multiply the value of AM by 2 and we'll get the length AB. So what is the size of AM? The size of AM, we will so we'll focus on triangle AMQ. On this triangle, triangle AMQ, here sinus 60 degrees equals to AM over AQ in the right triangle AMQ, sinus 60 degrees equals to AM over AQ. AM is the missing variable, so we leave it as it is, over AQ equals to 5. So we found out here that sinus 60 degrees is square root of 3 over 2, and it equals to AM over 5. So here we will multiply this equation by 5, and we will get that AM equals to 5 times square root of 3 over 2. But we want to find out the value of AB. The value of AB, when we know that AM equals to MB. So AM equals to 5 times square root of 3 over 2, and MB, that equals also to AM, it will be also equal to 5 times square root of 3 over 2. So we found out that AB equals to 2 times AM, that is actually 2 times 5 times square root of 3 over 2. 2 over 2 is 1, so 2 will get cancelled, and we found out that AB equals to 5 times square root of 3. Okay, AB equals to 5 times square root of 3. So here the area of triangle AQB equals to AB, that is actually equals to 5 times square root of 3 times MQ. MQ equals to 5 over 2. All divided by 2. Okay, so here 5 times 5 is 25, times square root of 3 over 2 times 2 is 4. So we actually found out that the area of triangle AQB, the area of triangle AQB equals to 25 times square root of 3 over 4 square units. That is to say, x equals to the area of triangle AQB, that equals to 25 times square root of 3 over 4. So again, the green shape equals to the area of the green shape equals to 2 times the area of segment AQB. That is to say, it equals to 2 times 25 pi over 3 minus x, and x is the area of triangle AQB, that equals to 25 times square root of 3 over 4 square units. I repeat again, the area of the green shape equals to 2 times the area of segment AQB, that is to say, it equals to 2 times the area of segment AQB equals to 25 pi over 3 minus 25 times square root of 3 over 4. Here we will take 25 we take out 25 as a common factor of those two expressions, and we will get that the area of the green shape equals to, so we took 25 out of those two expressions. It is 2 times 25. So what left from this expression after we took from it 25 as a common factor? What is left? It is actually pi over 3 minus, and what is left from this expression after we took from it 25 as a common factor? What is left? It is actually square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 2 times 25 is 50. It is 50 times pi over 3 minus square root of 3 over 4 square units. I'll repeat again. We found out, according to the first method, that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. We will do the same construction as we did in the first method, and we will define the center of this circle as point P. We will define the center of this circle as point Q. We will define the first intersection point between those two circles as point A, and we will define the second intersection point of those two circles as point B. We will join points P and B together, B and Q together, A and Q together, and A and P together by a straight line. I will not repeat on the things that we did in the first method. So here this equals to 5 units, this equals to 5 units. PQ also equals to 5 units. It is the radius of this circle. So here this equals to 5 units, also equals to 5 units. Triangle APQ is an equilateral triangle because of the fact that all of its sides are equal to each other, they are equal to 5 units. And triangle PQB, it is also an equilateral triangle, all of its sides are equal to 5 units. Actually, triangle APQ is congruent to triangle BPQ, according to side rule. I'll repeat again. Those two triangles congruent to each other according to side rule. All of their sides are equal to 5 units. And from the fact that those two triangles congruent to each other, we will conclude that the area of the equilateral triangle APQ is equal to the area of the equilateral triangle PBQ. Okay, we will conclude that the area of triangle APQ is equal to the area of triangle BPQ, because of the fact that those two triangles congruent to each other, they also have the same areas. So the area of those two triangles will be equal to the area of triangle APQ times 2. Okay, the area of those two triangles will be equal to the area of triangle APQ times 2. I'll write it down. So the area of this shape, that is actually the area of those two equilateral triangles, will be equal to 2 times the area of the equilateral triangle, triangle APQ. So the area of this shape will be equal to the area of those two triangles plus the area of segment AQ plus segment BQ plus segment PB plus segment AP. Okay, so I will write it down. The area of the green shape will be equal to 2 times the area of those two triangles, will be equal to the area of those two triangles, and the area of those two triangles is equal to 2 times the area of triangle APQ, because of the fact that those two triangles can go into each other. They also have the same area, so if we multiply the area of this triangle by 2, we'll get the area of those two triangles, plus, so the area of the green shape equals to the area of this equilateral triangle times 2 plus the area of segment AQ plus the area of segment BQ plus the area of segment PB plus the area of segment AP. I will repeat again. The area of the green shape will be equal to 2 times the area of the equilateral triangle, triangle APQ, 2 times the area of this triangle, plus the area of segment AQ, plus the area of segment QB, plus the area of segment PB, plus the area of segment AP. Again, the area of the green shape equals to 2 times the area of the equilateral triangle, triangle APQ, plus the area of segment AQ, plus the area of segment BQ, plus the area of segment PB, plus the area of segment AP. Okay? So, what is the area of triangle APB? What is the area of this triangle? We know that all the angles here are equal to 60 degrees because of the fact that it is equilateral triangle. All of its angles are equal to 60 degrees. This point is point M. Actually, we have already found out in the first method that AM equals to 5 times square root of 3 over 2, and those angles, of course, are right angles. PQ also equals to 5 units. So the area of triangle APQ will be equal to the base of the triangle, that is actually PQ, times the height to the base, that is actually AM, over 2. Again, the area of triangle APQ equals to the base PQ times the height of the base, that is AM, over 2. But PQ equals to 5 units, AM equals to 5 times square root of 3 units, 5 times square root of 3 units over 2, all divided by 2. So we actually found out that the area of triangle APQ equals to PQ, that is 5, times AM, that is 5 times square root of 3 over 2, all divided by 2. So 5 times 5 is 25, times square root of 3 over 2 times 2 is 4. So the area of triangle APQ is equal to 25 times square root of 3 over 4, and 2 times the area of triangle APQ, it is 2 times the area of triangle APQ, that is equal actually to 25 times square root of 3 over 4 units, plus the area of segment AQ. What is the area of segment AQ? The area of segment AQ equals to the area of sector APQ minus the area of triangle APQ. So the area of segment AQ will be equal to the area of sector APQ. The area of sector APQ will be equal to pi r squared times 60 degrees over 360 degrees, pi r squared times 60 degrees over 360 degrees, minus the area of triangle APQ, that is actually equals to 25 times square root of 3 over 4. So here r equals to 5, so r squared is 25. So in the numerator we have 25 pi, 60 over 360 is 1 over 6, so it is the area of sector APQ equals to 25 pi over 6 square units minus the area of triangle APQ, that equals to 25 times square root of 3 over 4 square units. So in conclusion, we found out that the area of segment AQ equals to 25 pi over 6 minus 25 times square root of 3 over 4. And what is the area of segment BQ? The area of segment BQ the area of segment BQ, the area of this segment will be equal to the area of sector PQB the area of this sector PQB minus the area of triangle PQB. So the area of segment PQ, the area of segment BQ equals to the area of sector PQB minus the area of triangle PQB. The area of sector PQB, this sector equals to pi r squared times 60 degrees over 360 degrees. It equals to pi r squared over 60 degrees over 360 degrees. And the area of triangle PQB, we have already found out that the area of triangle PQB equals to the area of triangle APQ. And the area of triangle APQ equals to 25 times square root of 3 over 4. So the area of segment PQB is pi r squared 60 degrees over 360 degrees. R equals to 5, so r squared is 25. So in conclusion, we found out that the area of segment BQ equals to 25 pi over 6 minus 25 times square root of 3 over 4 square units. So as you can see here, the area of segment AQ also equals to 25 pi over 6 minus 25 square root of 3 over 4. So the area of segment AQ equals to the area of segment BQ. The area of segment AQ equals to the area of segment BQ and if we continue to calculate the areas of segment PB and the area of segment AP, we will get the same result. That is to say, it will be also equal to the area of AQ. Therefore, the area of those four segments, segment AQ plus segment QB plus segment PB plus segment AP, will be equal to 4 times the area of segment AQ, because of the fact that the areas of those 4 segments are equal to each other. So we will multiply the area of segment AQ by 4 and we will get the area of those 4 segments. Okay, so actually the area of the green shape will be equal to 2 times the area of triangle APQ, as we have already found out, and it is actually equals to 2 times 25 times square root of 3 over 4 plus 4 times the area of segment AQ. The area of segment AQ and what is the area of segment AQ? We have already found out that the area of segment AQ equals to 25 pi over 6 minus 25 times square root of 3 over 4. So this is the area of segment AQ, and we have to multiply the area of segment AQ by 4, and we will add it to the 2 times the area of triangle APQ, and we will get the area of the green shape. So here we will get that the area of the green shape equals to 2 times 25 is 50. So it is 50 times square root of 3 over 4 plus 4 times 25 is 100. So we have here 100 pi over 6. 4 times minus 25 is minus 100 times square root of 3 over 4. So the area of the green shape equals to 50 minus 100 square root of 3 over 4 is minus 50 times square root of 3 over 4 here. 50 times square root of 3 over 4 minus 100 times square root of 3 over 4 equals to minus 50 times square root of 3 over 4, and we have to add also 100 times pi over 6. Here we divide both the numerator and the denominator of this expression by 2. 100 over 2 is 50. So it is 50 pi. 6 over 2 is 3. Plus minus 50 times square root of 3 over 4. So here we will take 50 as a common factor out of these expressions. So what is left from this expression after we took from it 50 as a common factor? What is left? It is actually pi over 3. And what is left from this expression after we took from it 50 as a common factor? What is left? It is actually square root of 3 over 4. So in conclusion, we found out that the area of the green shape, according to the second method, equals to 50 times, it equals to 50 times pi over 3 minus square root of 3 over 4 square units, and this is exactly the result that we found in the first method. So in the next step, I will summarize the lecture. Actually, we wanted to find out the area of this green shape. And we found the area of this green shape in 2 different methods. In the first method, I actually explained what is the definition of a sector and segment. So here, but I also repeat on the questions. We have here 2 circles. Each circle is passing from the center of the other circle, and we know that the radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So in the first step, I explained to you what is the meaning of a sector. Here, the area that is bound by 2 radiuses and the arc that is between those 2 radiuses is defined as a sector. So sector A or B equals to the area of this green shape, that is actually the area that is bound between radius AO and radius OB and arc AB. So this is the area, the green shape is the area of sector AOB. And the area of sector AOB equals to pi r squared times 60 degrees over 360 degrees. Okay, the r is the radius of the circle, and 60 degrees is the angle that is between those two radiuses. And the area and the angle between those two radiuses, it is not necessarily 60 degrees, it could be any angle between 0 to 360 degrees. And so I put here 60 degrees for this our specific example, but the angle between those two radiuses could be any other angle. So the area of sector AOB equals to pi r squared times the angle that is between those two radiuses over 360 degrees. And in this specific case, the area of sector AOB equals to pi r squared times 60 degrees over 360 degrees when r equals to the radius of this circle. Okay, so this is the definition of a sector. And then I presented to you the definition of a segment. So here the area in the green color, that is actually the area between the area that is bounded between chord AB and RKB. The area that is bounded between RKB and chord AB is defined as segment AB. Again, the area that is bounded by chord AB and RKB is defined as a segment. So AB is a segment of this circle, and the area of a segment equals to the area of sector AOB minus the area of triangle AOB. Again, the area of the sector AB in the green color equals to the area of segment AB in the green color equals to the area of sector AOB minus the area of triangle AOB. Okay? So you have to find out the area of sector AOB, and then you will subtract from the area of sector AOB the area of triangle AOB, and you will get the area of segment AB. Okay? Then we actually made the construction here. We joined points B and Q, points P and B, points A and P, points A and Q by straight line. All those line segments that we created are the radiuses of those circles. BQ is the radius of this circle because of the fact that it starts from the center of the circle, that is to say from point Q, and ends at point B, that is the point of the circle itself. Therefore it is defined as the radius of this circle, that is to say it equals to 5 units. The same thing is true about line segment PB. It is the radius of this circle because of the fact that it starts from point P and ends at point B, that is the point of this circle itself. Therefore PB is the radius of this circle, that is to say it equals to 5 units. And the same thing is true about AP and AQ. They are also the radiuses of those circles, therefore they are equal to 5 units. So here we actually created rhombus. Quadrilateral APBQ is a rhombus, and the definition of a rhombus is a quadrilateral that has four equal sides. A quadrilateral that has 4 equal sides is defined as a rhombus. So quadrilateral APBQ is a rhombus. Then we joined together points A and B by a straight line. So here I repeat again that quadrilateral APBQ is a rhombus, and then we join together points A and B by a straight line. AB is one diagonal of rhombus APBQ, and we join together points P and Q together. We join points P and Q together by a straight line. PQ is the second diagonal of this rhombus, and we have two characteristics that is true for the diagonals of a rhombus. The two characteristics that is true for the diagonals of a rhombus is that the diagonals of a rhombus are, first of all, perpendicular to each other. That is to say, the diagonal AB is perpendicular to PQ. It means that those two angles are right angles, and it is also true to say that PQ is perpendicular to AB. Therefore, we have in the intersections of those two triangles, we have here four right angles. 1, 2, 3, 4. All those angles are right angles. Why? Because of the fact that the diagonals of a rhombus are perpendicular to each other. So we have here four right angles. Okay? And the second characteristic of a rhombus is that they bisect each other. The diagonals of a rhombus bisect each other. That is to say, AB bisect PQ. It means that PM equals to MQ. Because of the fact that AB bisects PQ, that is to say, PM equals to MQ. And also, it is also true to say that PQ bisects AB. That is to say, AM equals to MB. Okay, AM equals to MB. Okay, but we know that PQ is the radius of this circle. Why? Because it starts from the center of this circle, that is to say from point P, and ends at point Q, that is a point of this circle itself. That is to say, PQ is the radius of this circle, that is to say, PQ equals to 5 units, PQ equals to 5 units from one side, but from the other side, because of the fact that the diagonal AB bisects PQ, it means that PM equals to MQ. PM equals to MQ. So if we define PM as X, then MQ will be also equal to X. So here we know that X plus X equals to PQ. X plus X equals to PQ. That is to say 2X equals to PQ. And PQ equals to 5. That is to say 2X equals to 5 units. And then we divided this equation by 2, and we got that X equals to 5 over 2, so PM that equals to X equals to 5 over 2, and MQ that equals to X equals also to 5 over 2. Okay? Then we actually we focused on four right triangles: the right triangle APM, the right triangle AMQ, the right triangle BQM, and the right triangle PMB. On those four right triangles, we calculated the values of those four angles: 1, 2, 3, 4. And the values of those four angles in those four right triangles, triangle APM, triangle AMQ, triangle MQB, and triangle PMB, on those four right triangles, those four angles, 1, 2, 3, 4, is equal, so the cosine of those four angles equals to 5 over 2 over 5. According to the definition of cosine, the cosine of those four angles, 1, 2, 3, 4, equals to 5 over 2 over 5. In all the four right triangles, the cosine of those angles is equal to 5 over 2 over 5. Okay? So, cosine of those four angles equals to 5 over 2 over 5. 5 over 2 over 5 is 5 over 5 times 2. 5 over 5 is 1, so we found out that cosine of those four angles equals to 1 over 2. If cosine of those four angles equals to 1 over 2, it means that each angle of those four angles are equal to 60 degrees. So all those four angles, they are equal to 60 degrees. They are equal to each other and they are equal to 60 degrees. So we found out that those four angles are equal to 60 degrees. Then we actually proved the triangle APB is congruent to triangle AQB. Triangle APB, this triangle congruent to this triangle, triangle AQB. Why they congruent to each other? Because AP equals to AQ equals to 5 units, AP equals to AQ equals to 5 units, PB equals to QB equals to 5 units, and AB equals to itself. It is a common side, it belongs to both triangles, so AB equals to AB is a common side. So we found out that triangle APB congruent to triangle AQB according to side rule. So those two triangles congruent to each other. From the fact that those two triangles congruent to each other, we will conclude that they also have the same areas. That is to say, the area of triangle APB is equal to the area of triangle AQB. So those two triangles have the same areas. Okay? Then, what is the area of segment APB? The area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. Again, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. So the area of sector AQB, what is the area of sector AQB? The area of this sector, it will be equal to pi r squared times 120 degrees over 360 degrees. The area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. R equals to 5, so r squared is 25. So in the numerator we will have pi r squared, that is 25 pi, and 120 degrees over 360 degrees is 1 over 3. So in conclusion, we got that the area of sector AQB equals to 25 pi over 3. Again, the area of sector AQB equals to 25 pi over 3. Then we calculated the area of sector APB. What is the area? Actually, we calculated the area of sector APB. What is the area of this sector? The area of sector APB will be equal to pi r squared times 120 degrees over 360 degrees. Again, the area of sector APB equals to pi r squared times 120 degrees over 360 degrees. Area of sector APB equals to pi r squared times 120 degrees over 360 degrees. So the area of sector APB, r equals to 5. So r square is 5 square, 5 square is 25. So in the numerator we have 25 pi, and 120 degrees over 360 degrees is 1 over 3. So we found out that the area of sector APB also equals to 25 pi over 3. And it is exactly like the area of sector AQB that is also equals to 25 pi over 3. So from those two equations, we conclude that the area of sector APB equals to the area of sector AQB. Okay? So we found out that the area of sector APB is equal to the area of sector AQB, and both equals to 25 pi over 3 square units. And we actually found out that the area of those two triangles are also equal to each other. Here we found out that the area of triangle APB is equal to the area of triangle AQB. Okay, so we found out that the area of triangle APB is equal to the area of triangle AQB. We define the area of X, the area of those two triangles as X. So the area of those two triangles is equal to X according to our definition. And the area of sector APB equals to the area of sector AQB, that equals to 25 pi over 3 square units. Then, what is the area of segment APB? The area of segment APB, the area of this segment APB is the green shape that is like half a circle, like a semicircle. So the area of this segment APB will be equal to the area of sector AQB minus the area of triangle AQB. Again, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. Okay? And we have already found out that the area of sector AQB equals to 25 pi over 3, and the area of triangle AQB is equal to X according to our definition. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus X square units. Then, what is the area of segment AQB? The area of this segment, it is actually the shape in the green color that is like a semicircle. The area of this segment AQB will be equal to the area of sector AQB, the area of sector APB minus the area of triangle APB. Okay, so the area of segment AQB equals to the area of sector APB minus the area of triangle APB. And we have already found out that the area of sector APB equals to 25 pi over 3 square units, and the area of triangle APB equals to X according to our definition. That is to say, we found out that the area of segment AQB equals also to 25 pi over 3 minus X, exactly like the area of segment APB that is also equal to 25 pi over 3 minus X. So we actually found out, in conclusion, that the area of segment APB is equal to the area of segment AQB, because the area of those two segments are both equal to 25 pi over 3 minus X square units. Okay? And because of the fact that the area of segment AQB is equal to the area of segment APB, we can find out the area of one segment, and we will multiply it by 2, and in this way we will get the area of the green shape, because of the fact that those two areas, they are equal to each other. Okay, so we will multiply the area of segment AQB by 2, and in this way we will get the area of the green shape. Why? Because those two areas are equal to each other, therefore we can take one segment and we'll multiply it by 2, and we will get the area of this green shape. So the area of the green shape will be equal to 2 times the area of segment AQB. And 2 times the area of segment AQB, we know that the area of segment AQB equals to 25 pi over 3 minus X. So we have to multiply it by 2, and in this way we will get the area of the green shape. And X is the area of triangle AQB. X is the area of triangle AQB. So what is the area of triangle AQB? We have already found out that in the first method that AM equals to 5 times square root of 3 over 2. PQ is the radius of this circle, that is to say it equals to 5 units. So the area of triangle PQB equals to the base of the triangle that is PQ times the height to the base that is AM over 2. Again, the area of triangle AQB equals to the base of the triangle that is AB times the height to the base that is MQ over 2. And AB, again, the area of triangle AQB equals to the base of the triangle that is PQ, the base of the triangle no, actually the area of triangle AQB, again the area of triangle AQB equals to the base of the triangle, that is actually AB, times the height to the base, that is MQ, times 2. And we have already found out that AM equals to 5 times square root of 3 over 2. And we know that AM equals to MB because of the fact that the diagonals of a rhombus bisect each other. That is to say, AM equals to MB. So if AM equals to 5 times square root of 3 over 2, then MB will be also equal to 5 times square root of 3 over 2. So AB equals to 2 times 5 square root of 3 over 2, and 2 times square root of 3 over 2 equals to 5 times square root of 3. So AB, that is the base, equals to 5 times square root of 3 times the height, that is QM. QM equals to 5 over 2. So it is 5 times square root of 3, that is the base, times the height, that is 5 over 2, all divided by 2. So here we have 5 times 5 is 25, times square root of 3 in the numerator, and in the denominator we have 2 times 2. So in conclusion, we found out that the area of triangle AQB equals to 25 times square root of 3 over 4 square units. And then we found out here sinus 60 degrees equals to, so we calculated it again, sinus 60 degrees equals to AM, here sinus 60 degrees. In order to find out the value of AM, we did sinus 60 degrees equals to AM over 5, AM over 5. We know that sinus 60 degrees is square root of 3 over 2, so we multiplied this equation by 5, and we got that AM equals to 5 times square root of 3 over 2, and because of the fact that AM equals to 5 times square root of 3 over 2, then 2 times AM will be equal to 2 times 5 square root of 3 over 2, 2 over 2 is 1, so we found out that AB equals to 5 times square root of 3, and because of the fact that AB, that is the base of triangle APQ, equals to 5 times square root over 3, that is the value of AB, and the height QM equals to 5 over 2, all divided by 2, so we got to the result that the area of triangle AQB equals to 25 times square root of 3 over 4, and then, so we know that the area of triangle AQB equals to 25 times square root of 3 over 4 square units. Again, the area of triangle AQB equals to 25 times square root of 3 over 4 square units. And the area of the green shape equals to 2 times the area of segment AQB. Okay? And we have already found out that the area of segment AQB equals to 25 pi over 3 minus 25 times square root of 3 over 4. So here we took 25 out of these two expressions as a common factor. So here we have 2 times 25, and inside the brackets we left with pi over 3 minus square root of 3 over 4. 25 times 2 is 50. So we found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. This is according to the first method. Then I presented to you how to find out the area of the green shape according to the second method. In the second method, we did the same construction as we did in the first method. We have here two equilateral triangles. Triangle APQ is an equilateral triangle because of the fact that all of its sides are equal to each other. And triangle PQB is also an equilateral triangle because of the fact that all of its sides are equal to each other. Those two triangles can go into each other according to side rule. And because of the fact that those two triangles can go into each other, they have also the same areas. So the area of triangle AQP is equal to the area of triangle PQB. Okay? Then, what is the area of the green shape? So the area of those two triangles will be equal to the area of triangle AQP times 2 because of the fact that the area of those two triangles are equal to each other. So the area of the green shape will be equal to 2 times the area of triangle AQP times the area of segment AQ plus segment BQ plus segment PB plus segment AP. Again, the area of the green shape equals to 2 times the area of triangle APQ plus the area of segment AP plus the area of segment BQ plus the area of segment PB plus the area of segment AP. Okay, so the area of triangle APQ, the area of this triangle APQ will be equal to PQ times AM. PQ is the base. The area of this triangle APQ will be equal to the base of the triangle that is PQ times the height that is AM divided by 2. The area of triangle APQ equals to the base of the triangle that is PQ times AM that is the height over 2. PQ equals to 5 units. We have already found out in the first method that AM equals to square root of 5 times square root of 3 over 2, all divided by 2. So in conclusion, we found out that the area of triangle APQ equals to 5 times 5 is 25. So in the numerator we have 25 times square root of 3 over 4. So the area of triangle APQ, the area of this triangle, the equilateral triangle APQ, equals to 25 times square root of 3 over 4. So we actually found out that the area of triangle APQ equals to 25 times square root of 3 over 4. So we have to multiply it by 2. And we also have to find out the area of segment AQ. The area of segment AQ, the area of this segment will be equal to the area of segment of sector APQ minus the area of triangle APQ. Again, the area of segment AQ will be equal to the area of sector APQ minus the area of triangle APQ. What is the area of segment APQ? The area of this segment APQ will be equal to pi r squared times 60 degrees over 360 degrees. Again, the area of segment sector APQ will be equal to pi r squared times 60 degrees over 360 degrees. And we also found out the area of triangle APQ. We have already found out that it is equal to 25 times square root of 3 over 4. So in conclusion, we found out that the area of segment AQ equals to 25 pi over 6 minus 25 square root of 3 over 4. Then we calculated the value of segment, the area of segment BQ, the area of this segment BQ. The area of segment BQ will be equal to the area of sector PBQ minus the area of triangle PBQ. Again, the area of sector BQ will be equal to the area of segment BQ will be equal to the area of sector PQB minus the area of triangle PQB. The area of sector BQ equals to pi r squared times 60 degrees over 360 degrees minus the area of triangle PQB. The area of triangle PQB, the area of triangle PQB is equal to the area of triangle PQA. That is to say, the area of triangle PQB will be also equal to 25 times square root of 3 over 4. So we got, in conclusion, that the area of segment QB or BQ equals to also 25 pi over 6 minus 25 times square root of 3 over 4. So we actually found out that the area of segment AQ is equal to the area of segment BQ. And if we continue to calculate the area of segment PB and the area of segment AP, we will get to the conclusion that they also have the same areas of segment AQ. Therefore, we can take the area of segment AQ, we will multiply it by 4, and in this way we will get the areas of those 4 segments, 1, 2, 3, and 4. Okay, so we actually found out that the area of the green shape equals to 2 times the area of triangle APQ, that is actually 2 times 25 times square root of 3 over 4, times 4 times the area of segment AQ. And we have already found out that the area of segment AQ equals to 25 pi over 6 minus 25 square root of 3 over 4. So here 2 times 25 is 50, so we got here 50 times square root of 3 over 4. And 4 times 25 is 100, so we got here that is this expression equals to 100 times pi over 6 minus 4 times minus 25 is minus 100 times square root of 3 over 4. So we have here 50 times square root of 3 over 4 minus 100 times square root of 3 over 4. That is to say, it equals to minus 50 times square root of 3 over 4. And here we divided both the numerator and the denominator of this expression by 2, and 100 over 2 is equal to 50, and 60 over 2 is 3. So in conclusion, we got that the area of the green shape equals to 50 pi over 3 minus 50 times square root of 3 over 4. Here we took 50 as a common factor out of these two expressions. And inside the brackets, what is left from this expression is pi over 3, and what is left from this expression after we took from it 50 as a common factor is actually minus square root of 3 over 4. So in conclusion, we found out that the area of the green shape according to the second method equals to 50 times pi over 3 minus square root of 3 over 4 square units, exactly as we found out in the first method. Okay? Thank you very much.